So good morning, afternoon, wherever you are. So last week we were studying the GKR protocol, which is made possible by the sumcheck protocol, which the prover and verifier run over a gate at each layer. I think the GKR protocol is maybe a step up in difficulty. I have some questions about how the soundness of each layer works, but maybe I could hand the floor over to Justin to introduce the chapter.
Cool, thanks. I'm also slightly less prepared this week with the holiday, but yeah, I think we're good. So maybe a quick review of a concept, like a really important perspective that really came up last week, especially with the counting triangles protocol, because this perspective is also taken in the GKR protocol and pretty much any like doubly efficient interactive proof. So, anything that in the book other than the Sharp-SAT protocol, this perspective comes up. So here's the perspective. So given like a vector of length n, where each entry of the vector is a field element, what we often do when designing interactive proofs is we don't really view that vector as a vector. Instead, we view it as a function mapping the Boolean hypercube to the field. And what that means is if the vector has length n, then we view the vector as like the list of all evaluations of some function, mapping 0, 1 to the log n to the field. So like the first entry of the vector is the function evaluated at 0, 0, 0, log n zeros. The next one is the evaluation of the function at 0, 0, 0, 1, then 0, 0, 0, 1, 0, and then 0, 0, 0, 1, 1. So you wind up viewing the vector like not as a vector, but really as a function with domain 0, 1 to the log n. And the reason you do that is because any function over that domain has a unique multilinear extension polynomial. And with that, that's what we mean when we say, here's some vector of length n, consider its multilinear extension, right? We mean view the vector as a function over domain 0, 1 to the log n, and then take the unique multilinear extension polynomial of that function. So when we're looking to, apply the sumcheck protocol to solve some problem, what we typically do is, take one or more of these multilinear extension polynomials and somehow kind of put them together to get a single polynomial that's no longer multilinear, but is very low degree in each variable, often 2 or 3 degree variable, and such that summing the evaluations of that polynomial over the Boolean hypercube gives you the desired answer. So in the counting triangles protocol of last week, what we did was, the input was like an n by n matrix with ijth entry interpreted as like indicating whether or not vertex I is connected to vertex j in the graph, right? And we did this thing of like viewing that as a function over the domain of the Boolean hypercube, taking the multilinear extension of that, and then we sort of took the product of 3 copies of that. And that actually gave us an extension polynomial it extended the function that took as input 3 gate labels, three vertex labels from the graph, and spit out one if and only if they formed a triangle. So that means like summing up all evaluations of that polynomial, over the Boolean hypercube, 0, 1 to the 3 log n's, sum up the number of triangles in the graph. Okay. Questions?
Yeah, I just want to make sure that I understand correctly. So viewing a function viewing a vector as a function, the function that we construct by Lagrange interpolation, allows us to do verification of the function by sumcheck, because we look at the evaluation, or we look at that vector as the sum of all evaluations of that function. So by summing all of the evaluations of that function with, for instance, we get back the vector, which allows us to sort of do this GKR protocol, which allows us to do sumcheck protocol to verify the subvector is subvector as the evaluation of subfunction, the sum of the evaluations of subfunction. Is that roughly correct?
It sounded, I guess maybe half correct. So let me try to sort of repeat in my own words with some slight differences, which might have just been preference about language semantics. But like the key issue, the reason we're dealing with these extension polynomials at all is the following. And there was some discussion of this in the chat. the sum check protocol, what that's capable of doing is summing up all evaluations of some low degree polynomial over the Boolean hypercube. And often, when you just the verifier, the problem the verifier is interested in solving in these protocols, there is some function. It's not a polynomial. There's some function that the verifier is interested in summing up all evaluations of that function over the hypercube. So, like for the counting triangles problem, that function is the function that takes as input three vertex labels and spits out one if and only if they form a triangle, right? So like computing the number of triangles in a graph is like summing over all triples of vertices and, like adding one to the sum if they form a triangle. So that's what the verifier like really wants to do, is just sum up all evaluations of that function, which maps vertex triples to, is this a triangle or not? To use the sum check protocol to solve the problem, we need to identify a low degree polynomial such that summing up the evaluations of that polynomial is equivalent to summing up the evaluations of that function. Right. And so now you have to play the following game. You have to identify a low degree polynomial that has that property, that summing up its evaluations is the same as summing up like the desired function's evaluations. And that's why we're interested in extension polynomials, right? Because that sort of just gives you a polynomial that agrees with the function you're extending at all Boolean inputs. It's sort of by definition exactly the kind of polynomial. We need it to be low degree in each variable, and we need the verifier to be able to evaluate that polynomial quickly at a random. And that last part is also why the polynomials we apply sum check to are typically not themselves multilinear, but rather are obtained by sort of taking one or two or three multilinear polynomials and producting them together or something like that. So typically it turns out that if you literally just like sort of took the bare function the verifier wants to sum up the evaluations of and took the multilinear extension of that, often evaluating that multilinear extension at a single point is just as hard as computing the whole sum. And there's an exercise on this chapter that walks you through exactly that situation for like satisfiability problems, like the sharp-set protocol that we saw last week. So what's going on here? So sorry for all that background and aside. To summarize, I guess. Essentially, the way we get the polynomials we want to apply sum check to always involves taking some multilinear extensions of things, right? And those things are often specified to the verifier as just a vector of length n, and we just want to take the multilinear extension of that vector, meaning you view the vector as not really a vector of length n, but rather as a function on log n bits, and so that. And the key point is that ensures that summing up all evaluations of that multilinear extension, although again, when we finally apply sum check, it'll really be to some sort of derived non-multilinear polynomial, is equivalent to summing up the evaluations of the vector. So yeah, where things get confusing and is just the fact that the polynomials we wind up applying sum check to are not themselves multilinear extensions. They're always obtained by taking the multilinear extension of like two or three different things and producting them together. So that's I think that's the source of all confusion, and like sort of what your question was maybe really about in the end was I think you were using language of the form like summing up all evaluations of the multilinear extension is equivalent to like just computing the sum of all entries of the vector. That is true, but in the actual application of the sum check protocol, the thing we actually wind up summing up all evaluations of is not actually multilinear. It's like a product of a handful of multilinear things. I'm done talking. You should ask follow-up.
Yeah, just one follow-up was just, and the power of the verifier or the power of the protocol is for the verifier to be able to basically send random bits, random noise, is not confined to the original domain of 0, 1, and have the prover basically demonstrate knowledge of the full function through successfully providing answers to those questions. Is that a correct interpretation?
Yeah, I think that's exactly the right intuition. And yeah, that general technique, that intuition that you just captured of like the power being that, these multilinear extension polynomials, or, extension polynomials in general, they're sort of like extending the domain of the function you care about from 0, 1 to the log n to field to the log n. And field is, think of it as vastly bigger than just it contains 0, 1 and a few bunch of other field elements. And yeah, this is called like arithmetization or algebraization. It's one of the most celebrated techniques in all of theoretical computer science. And that's exactly like the verifier's power to like catch the prover if it deviates in any tiny way is exactly coming from that. And it's really sort of intuitively the distance amplifying properties of, these low degree extension encodings, which we've talked about in previous weeks, how you can sort of, if you view the polynomials as like a giant vector consisting of all evaluations of the whole polynomial, that's like a much, much longer vector than the length n vector you started with. That encoding transformation from the length n vector to the giant vector is distance amplifying. That's like basically the Schwarz-Zippel lemma. The distance amplifying properties of the code just sort of kind of blow up tiny deviations of the prover from like how it should be behaving and sort of blows them up into highly detectable things, which ensures that like no one, not even the prover, ever really needs to fully quote materialize these giant vectors even in their own heads. They sort of only randomly, the verifier is kind of randomly picking entries of these encodings to kind of spot check the prover's claims. And so the distance amplifying properties mean if the prover cheats even a little bit, sort of even just like randomly spot checking the claims is enough to pick up the deviation. Thor, did my rambling help sufficiently?
I think it may have. I think I'm going to leave room for other people to ask questions before I keep going. So open the floor.
Since people don't seem to be jumping at the bit, maybe let me try one more time to say something clearer and more succinct in response to your question, Thor. Like if the verifier was somehow like given a vector of length n, okay, and the verifier's goal was to just sum up all entries of that vector, okay, then I think everything you said was like totally accurate, like verbatim, in the sense that you could solve that problem as follows: like take the multilinear extension of that vector, apply the sum check protocol to that polynomial. Okay, and the total communication cost of that protocol would be logarithmic in n. Because the multilinear extension has log n variables to degree 1 in each variable. But at the end of the protocol, the verifier would have to evaluate that multilinear extension at a random point, which it could do in sort of the fastest time you could possibly hope for, which is linear time, meaning, to have any idea what is the multilinear extension of that function to evaluate it at even a single point, the verifier has to at least read the description of the function, which requires, reading every entry of this vector of length. And in fact, there's a lemma 3.8 or whatever in the book says the verifier can evaluate the multilinear extension of the vector, at any desired point in the field, in linear time. So that's great. That gives you an interactive proof for summing up all entries of the vector. However, it's just not an interesting interactive proof because the verifier could ignore the prover and in the same amount of time, sum up all the entries of the vector, right? Just by streaming, making one pass over the vector and computing the sum of all the entries, right? So what was the point? So when we actually use the sum check protocol, what we're sort of doing in the end is we wind up, conceptually, you could think of it as the vectors that we want to sum up a vector with a huge number of entries. It doesn't have to be an exponential number of entries. It could be, in terms of the size of the input, it could be n squared entries. In the counting triangles protocol, it's n cubed entries, right? Like the vector we really want to sum up all evaluations of is the vector of length n cubed, which has one entry for every triple of vertices. And that entry is a 1 if and only if they form a triangle. Okay, and the real goal then is to identify a polynomial extension of that vector of length n cubed, which the verifier can evaluate at a random point in time much less than n cubed. Okay, because if it if it took n cubed time to evaluate the extension polynomial of that vector at a random point, then there'd be no point to the verifier like using a prover to do the hard work, right? The verifier could just solve the counting triangles problem in n cubed time on its own. And there's in fact an exercise in the book about exactly that question. So from that perspective, the real goal is to, come up with a low degree extension polynomial of this like length n cubed vector. Again, we're going to wind up thinking of that as a function over, 3 log n bit, such that the verifier can evaluate that extension polynomial in linear time order, and well, in the case of triangles, it's n squared. That n squared is the size of the input in that case, if it's an n vertex graph, rather than n cubed, to ensure that the verifier is like saving time compared to just solving the problem on her own. And the way we actually identify that extension polynomial, which is not itself multilinear, is we take the input vector, which has length only n squared, not n cubed, and we take its multilinear extension, and we sort of take 3 copies of it, if you will, and product them together. And what that does is it gives you a multi-quadratic, so degree 2 in each variable, extension polynomial of the length n cubed thing we actually want to sum. And the verifier can evaluate that quadratic extension polynomial in linear, in time n squared, because evaluating the product of 3 copies of the multilinear thing just requires evaluating the multilinear thing itself 3 different times. And each one of those can be done in time linear in the size of the input fed to the verifier. So maybe I should put something in the book about what I just said, but I hope that was helpful. Yeah.
Okay, so I think I got lost there at the end when you started talking about the the multi-quadratic. First, I think you said that we take 3 copies of the input variable and multiply them together, and you said it was a multi-quadratic, not multi-cubic. Can you explain that?
Yeah, sure. The graph theory problems are annoying because the input to the verifier is an n by n matrix, right? So like, whose ijth entry, it indicates whether vertex I and vertex j are connected to each other. And so like the real input size is n squared. So you just want to wind up with this annoying thing where, normally n denotes the size of the input to the verifier, but here like it's n squared. That's like the real size of the input. So I'm kind of using a shorthand, which is confusing when I say the product of 3 copies of the multilinear extension of the input. So what it actually is, like what that polynomial is, that multi-quadratic polynomial, it's the multilinear extension of the input matrix evaluated at like a comma b times the same thing but evaluated at b comma c times the same thing but evaluated at c comma a. Right. And that's indicating that's trying to indicate that A is connected to B, B is connected to C, and C is connected to A. And it's multi-quadratic because each one of those vertices appears twice. Sorry, you might hear a baby screaming upstairs. Apologies. And remember, these vertices, their labels consist of log n bits. So that means like each bit of each label is sort of appearing twice, right? Like A comma B, B comma C, C comma A, so like each bit of each of those labels appears twice. So that's where multi-quadratic is coming in. Does that make sense?
Yeah, I think I was just confused what you were referring to in that instance. I thought that in the naive counting triangles analysis that I did, it was the verifier time was O of n squared. That's what we're talking about, right?
Yeah, so the verifier time in the interactive proof is O of n squared, and like the naive algorithm that just counts all the triangles with no prover is O of n cubed. So an O of n squared time verifier is like, better than ignoring the proof, faster than ignoring the prover and solving the problem.
Wait, you said that ignoring the prover means that you just have a blow up of the factor of n in your asymptotic, right?
Yeah. What I'm saying is, I would, this interactive proofs are only interesting if they save work for the verifier compared to just the verifier solving the problem on her own with no, not talking to a prover in any way. And so I'm saying, if the verifier did just solve the problem on her own with a naive triangle counting algorithm, that's n cubed time in the interactive proof, the verifier runs an n squared time. So it is saving work. As another aside, even if the verifier didn't save work, the interactive proofs can still be useful once you start bringing cryptography in and the prover is proving knowledge of a witness satisfying some property. Then the interactive proof can, in that context, still be interesting, even if it doesn't save the verifier work. But that's a topic for later in the book.
Looks like 0xSage asked in the chat, in practice, how do we think about subtraction working within GKR? Since it's general purpose, are the gate orders swapped around by the compiler?
Yeah, there are a bunch of ways you could handle subtraction gates. One is you could have a separate subtraction operation that's treated sort of completely distinctly from addition, but then you'd have to modify the interactive so that it involves not just like, this add I function and this multi function that indicates, is this like an addition gate with given in neighbors, or but also add in a third function, subtract. If you didn't want to do that, if you just wanted to, just have addition and multiplication being like the only primitive operations in the circuit, I guess any subtraction would have to be, multiplied by -1 and then add. And if I wasn't so sleep deprived, I might be able to come up with like 2 or 3 alternatives even to those. So it's something you have to think about, like the best way sort of in practice to handle, so that you both don't pay like an efficiency cost for your, how expensive your implementation is, but also you as like the person implementing the protocol doesn't have to make your life so much harder by introducing like a third operation into the circuit and modifying the protocol to support it. But hopefully that gives you just a sense that, there are a bunch of things you could do and you're just going to have to weigh the annoyances of each. Cool. Okay. Yeah. Thanks so much for the question. It's a great question. More questions?
I have one that's a little bit of a dig at the kind of history of these protocols, because I think last week we talked about how, and in the book this is mentioned as well, there's a lot of work on these kind of protocols that were completely unrealistic computationally. And I'm curious in terms of how this work was developing over time. Was the original goal to develop? What is the kind of motivation of this branch of mathematics prior to becoming computationally, efficient to operate? Was it about setting up protocols for efficient, evaluation of truth between a prover and a verifier, or is there a more sort of theoretical motivation?
Yeah, it's a really interesting question and answer, because there were like a bunch of different motivations that sort of all came up. Some like really bizarre. It's bizarre that some of these, completely different motivations led to the same notion at the same time. So the very first 2 papers introducing interactive proofs or things like them, one of them, the notion of zero knowledge was introduced in the same paper. So like this idea of having an untrusted prover and you just want to save the verifier work so the verifier is as efficient as possible, and, maybe just reads the input and doesn't do much more things or something, has like nothing to do with zero knowledge, on its own. And yet the one paper introduced both these foundational notions. And I'm not actually sure I can say more about those authors' motivations off the top of my head than that they introduced both those, fundamental notions. The other paper at the same time, or at least that appeared in the same conference, completely different motivations. That was considering problems that were not known to be in NP, the complexity class NP. So they were not known to have static, efficiently checkable proofs, of like membership in the language. So this was Babai. He observed that if you allow just like one message of interaction, the bare amount of interaction for those problems, and also randomness for the verifier, so there's a small soundness error, he could give efficient proof systems for those languages. And so, I guess there's a notion of sort of work saving for the verifier by going to an untrusted prover there, but you sort of have to squint a little harder to see it. So those were the first 2 papers. And then when people introduced a related notion that we'll see in a few weeks called probabilistically checkable proofs, I think the original work on that did talk exactly about the sort of things we're talking about now, a very weak verifier sort of monitoring like a giant supercomputer, making sure that the giant supercomputer doesn't make any mistakes. I think that first paper introducing PCPs did have that explicit motivation. And then like everything else on PCPs that came after that had a totally different motivation. And in terms of things like proving that certain approximation problems are NPR, like, it shouldn't have any efficient algorithm. So the motivations for people studying this stuff, there's been like 3 or 4 of them. And I'd say once that PCP work came out and like the motivation switched towards this weird, like showing approximation problems are challenging thing, there wasn't many papers on our motivation, this work saving for the verifier and snarks and things, until right around 2007, 2008, when the GKR paper came out and, stuff on snarks started coming out and so forth. That's the end of my rambling. I hope that was helpful and interesting.
Thanks.
Yeah, this sort of thing, I guess, happens more often than you might otherwise expect, where like a bunch of different independent, people discover the same notion, often for like seemingly different reasons. I don't know. That's just some like quirk of mathematics in general. Maybe it just is because like powerful natural notions often have more than one perspective at which they're useful and worth understanding and stuff. It's in the ether. Yes, I agree. It's floating out there. Okay, so are there more questions? Should I now start rambling about the GKR protocol? Okay, I will take that as a yes. Okay, this is what I should have prepared a little and did not, but let me do my best. Okay, so the GKR protocol is an interactive proof for circuit evaluation. So in particular for arithmetic circuit evaluation, although if you, as we saw in the SharpSat section, if you had a Boolean circuit where the gates are like AND and OR gates, you can always turn that into like an equivalent arithmetic circuit, computing an extension polynomial of the Boolean circuit. And then you could like apply the GKR protocol to that arithmetic circuit. Okay, so yeah, the arithmetic circuit takes as input like n field elements and applies a sequence of addition and multiplication operations and spits out some output. It could spit out more than one output. And the way the GKR protocol works is the prover begins by sort of, telling the verifier the claimed outputs of the, and then, the verifier doesn't trust the prover's honest. So the verifier kind of starts interrogating the prover, and they wind up applying the sum check protocol, once, and that winds up, in a sense, reducing the prover's claim about the outputs of the circuit to a claim about the values of the gates feeding into the outputs. Right. But the verifier can't check that claim directly because, that would require knowing the values of the gates feeding into the outputs of the circuit. And like knowing the values of those gates is like just about as hard. It's only like slightly easier than figuring out what the outputs of the circuit themselves are, which is like us, solving the original problem with no prover. So the protocol sort of iterates, it like applies the sum check protocol again, and in the process reduces the claim about the gates feeding into the outputs to a claim about the gates feeding into those gates. And they proceed layer by layer of the circuit towards the input layer until at that point the prover is forced to make a claim about the inputs of the circuit, and the verifier can check that claim directly in linear time. So to be a little more precise about all of this, just to slightly more precise, what I will sort of unpack 2 parts of these statements I've made. So what do I mean when I say, we reduce a claim about the outputs to a claim about the gates feeding into the output? By that, I mean it is, quote, safe for the verifier to believe the claim about the outputs if the verifier is convinced about the claim involving the gates feeding into the outputs. So another way of saying that is, if the claim about the outputs was false, then with high probability over the choice of the verifier's random challenges, the prover would be forced to make a false claim as well about the gates feeding into the outputs. Right. So you're going layer by layer through the circuit, and like if the original claim about the gates feeding about the outputs of the circuit are false, right, then the prover is going to also, with overwhelming probability, be forced to make a false claim about the gates at the preceding layer, and then with high conditioned on that, with overwhelming probability, be forced to make a false claim about the gates feeding into those. and so on and so forth until you get to the input layer where the prover is still with overwhelming probability making a false claim. And the verifier checks that final claim about the inputs directly, so we'll pick up on the falseness of that claim. And the other thing I want to unpack is when I say, quote, a claim about the gates feeding into the outputs, and a claim about the gates feeding into those gates, and a claim about the input itself, what I really mean, what that claim actually is it's a claim regarding the multilinear extension of those gate values evaluated at a random point. Like that's actually what I mean, what the claim is. It's just, conceptually, you're envisioning the circuit, as arranged sort of layer by layer. And you're viewing, sort of the gates at each layer of the circuit. Each one has a value. So you're for each layer, you're just viewing there's a vector of gate values. That's it. And, as I rambled about for 20 minutes earlier today, given any vector of values in a field, there's a unique multilinear polynomial that extends that vector once you start viewing that vector as a function on sort of logarithmically many bits instead of just as a vector. So the prover in the protocol winds up making claims about just like the multilinear extension of each of these vectors of gate values, one per each layer. Okay, I can keep going, but let me pause, see if there are any questions at this point.
So is there a transformation from a polynomial to a layered circuit?
From a polynomial to a layered circuit. Can you maybe elaborate on what you mean by that?
Like we use the sum check protocol to do like polynomial evaluation. So is there a way to just convert this to maybe a circuit and run the GKR protocol, and it's somehow faster than this sum check protocol alone? I don't know if
No, I see what you're saying. Yeah. So you're imagining we sort of designed a sum check protocol to solve a problem. So we've identified some low degree polynomial G so that, the thing the verifier wants to know turns out to equal the sum of G's evaluations over the Boolean hypercube. And we could just apply the sum check protocol directly to G, but, is it ever better to instead identify an arithmetic circuit that sums up all of G's evaluations and then apply the GKR protocol to that circuit or something like that? And I think the answer is roughly no. The direct answer is no, in the sense that, the GKR protocol takes whatever circuit it's given that the verifier wants to evaluate, and it applies the sum check protocol many times, once per layer of the circuit. And so typically, that's going to be more expensive than a single invocation of the sum check protocol. So, it's often the case that if you give me a natural structured problem like counting triangles or, just something nice that people care about solving, it's often the case that, there's sort of two ways you could go about giving an interactive proof of that problem. One is the quote general purpose way, which goes through something like circuit evaluation and the GKR protocol, which is just identify a circuit that evaluates the function and apply the GKR protocol to force the prover to evaluate that circuit correctly. And the alternative would be to cook up, to sort of do the first, just cook up a polynomial G, so that directly computing the sum of G's evaluations over the Boolean hypercube gives you what the verifier wants. And in the cases that you are able to cook up such a G, that's typically much better. That's what you should do. In fact, there are a lot of papers out there in the literature that just sort of go through that. It can take a lot of cleverness to do that if you want to ensure that the verifier can evaluate G at a random point efficiently. So, the verifier in the sum check protocol applied to G is fast and stuff. So I think the high level takeaway from my rambling is kind of if you can avoid the general purpose technique of going through circuit evaluation and applying the GKR protocol, you probably should, because it's generally there are overheads to it. You're applying the sum check protocol once per layer of the circuit and stuff. And for a lot of simple, nice problems, you can avoid that. And you can just apply the sum check protocol directly once to one polynomial. It's just sometimes you can't do that, that direct approach, right? Basically, because any polynomial you come up with that has the property you need, that's summing up its evaluations over the Boolean hypercube, gives you the answer the verifier seeks. Just evaluating that polynomial at a random point is like as hard as solving the problem in the first place, in which case you're going to be forced to go through the circuit evaluation technique. Did that make sense?
Yes, thanks.
Other questions? Okay, I can try to unpack the protocol a little more with our remaining 15 minutes and try not to eat up the whole time with free associated ramblings.
I think my main sort of point, think the sort of like central point of confusion for me, or at least it's like the thing that I think the rest of the protocol sort of orbits around, is like this claim that evaluating some check at an arbitrary gate on layer I and then layer I plus one and all the way back up to the input layer gives the verifier enough information to sort of recursively check that the things that the prover said at each layer were correct. So I think like the main thing to wrap my head around, if I was to state it simply, is that running the sum check protocol on an arbitrary gate on each round gives the verifier enough information to guarantee that to probabilistically know that the prover didn't lie.
Yeah, great. So I think here's the key intuition. So, a lot of people, when they encounter the GKR protocol for the first time, will think, well, the verifier, so the prover winds up making a claim at each layer about a single evaluation of the multilinear extension of the gates at that layer. And this feels like the same as making a claim about the evaluation of a single gate at that layer. And then people, it's very confusing. Like, how can one gate at that layer be enough information to check the whole layer? And here's the key point. It's not a claim about a single gate at that layer. It's a claim about a single evaluation of the multilinear extension of the gate values at that layer. And once you move outside of the Boolean hypercube, you evaluate the multilinear extension polynomial outside of the Boolean hypercube. Okay, each one of those evaluations involves every single gate at that layer. So somehow by looking at a single evaluation of the multilinear extension at a layer, that sort of wraps up information, like combines information about every single gate at that layer. And so the verifier is really like not just sort of like, it's absolutely not just sort of picking a random gate at each layer and like checking that the prover's claim about that gate is correct. Like that would not work, right? Because the prover absolutely could be, sort of making a correct claim about every gate in the whole circuit except one gate, that totally screws up the whole evaluation. And if you literally just sort of like spot check a small number of gates of the circuit, you'll never pick up on that. You have to get very lucky to pick up on that. So that's not what happens. What happens is the verifier sort of spot checks claims about these distance amplified encodings of each layer, and each entry of that distance amplifying for each layer incorporates information about every single gate at that layer. Did that help?
Yeah, I think so. But I suppose that means that I don't actually understand what the verifier's random bit does.
Yeah, so the verifier's randomness at each layer, and it's not just one bit. It's like, at each layer, the verifier is picking the GKR protocol. It winds up being, 3 or 4 random field elements, right? So each one of those field elements is like logarithmically many bits. But anyway, if the field has size, polynomial on the size of the circuit or whatever. So what the verifier is roughly doing is
clarify that. I thought the verifier was picking a random gate at each layer. Is that incorrect?
That is incorrect, and that's what what I was trying to clarify before. No, it's picking for each layer of the circuit. The verifier winds up picking several random field elements. I'm sorry. There's like a tornado coming here and a baby one level above me. It's I'm very sleep deprived, so let me collect myself for 1 second. I'm sorry. Every time the GKR protocol invokes the sumcheck protocol, which is once per layer of the circuit, okay, it's applying the sumcheck protocol to a polynomial in, 3 log s variables. You think of that polynomial as sort of taking as input the labels of 3 different gates, like, 1 at layer I and 2 at layer I plus 1. And in each round of the sum check protocol, the verifier picks another random field element and kind of binds another variable of out of those, 3 log yes variables or whatever to that field element. Okay, so over the course of each invocation of the sum check protocol, the verifier, so conceptually the verifier is picking like 3 random gates, but they're not actually gates that it's picking. It's these field elements, right? So it's moving beyond. It's not picking random gates. It's working in the multilinear extension world. These multilinear extensions, kind of extend the domain of the functions of interest from just binary gate labels to the entire field. In the appropriate 3 log s dimensional space. So field of the 3 log s. So this is very different. This is what I'm trying to get at, and I'm just my language is sort of failing me today. It's very different than picking like a random gate or a random 3 gates or something at each layer, and like just spot checking that one gate was sort of executed correctly by the prover. That's not what's happening. What's happening is at each layer, the prover in its head has a vector of values, like 1 per gate at that layer, right? And then is sort of conceptually replacing that vector with this giant encoding of the vector, the multilinear extension encoding. This is a vastly bigger vector. Okay. And the verifier is conceptually kind of picking a random entry of that giant vector and sort of spot checking the provers, doing things correctly sort of at that one entry. But because the verifier has moved beyond the Boolean hypercube domain by picking random field elements instead of, just random bits. Right. By spot checking the prover's, correctness for that one entry of this amplified vector, vastly bigger than just the original vector of gate values, right? That one entry of the amplified vector winds up containing information, like every single gate at that layer contributes to that one entry. Did that help at all? Still confusing?
But clarifying one thing, when we were talking about the extension of these gates, so previously in the chapter, there was the basically formulas for replacing the binary operations and or with these multiplicative or arithmetic operations. Is that still consistent here when we're talking about the operation of these over these gates? Are these logic gates? Should we think about the extension as being composed of these basically arithmetic substitutes to the original binary operations?
No, unfortunately, I think not at all. So going from Boolean circuit to arithmetic circuit, computing an extension polynomial of the Boolean circuit is just different than what's happening in the GKR protocol. The GKR protocol would be like applied to an arithmetic circuit. So you can just so maybe that arithmetic circuit came from taking a Boolean circuit and turning it into an arithmetic one. But then you're going to apply the GKR protocol to that circuit to make sure that prover evaluated that circuit correctly at whatever the input defier cares about.
Only one layer. We're moving one layer beyond. We're abstracting that even further.
Yes. Yeah. So now you have that arithmetic circuit, right? And then you're looking at like a layer of that arithmetic circuit, right? And you're making, so each iteration of the GKR protocol, 1 per layer of that circuit, but it forces the prover to make a claim about the multilinear extension of, that layer's gate values at one random evaluation. And then again, the key point though is that, once you start evaluating that multilinear extension outside of the Boolean hypercube, right? Each of those evaluations winds up containing information, like every single one of the gates at that of the function being extended contributes to that evaluation, right? So that's why, like, if the prover lies about the value of even a single gate at that layer, making the prover make a claim about the multilinear extension of that layer's gate values will sort of identify the deviation with overwhelming probability, even though that's the distance amplifying magic of multilinear extensions, right? You change even one entry of the vector you're extending, and like almost every entry of the multilinear extension encoding has to change. Okay, there's a statement in the chat. It is the same as evaluating the interpolating polynomial of endpoints at a new point. The evaluation at the new point depends on all the other endpoints. That is exactly right. So when you look at Lagrange interpolation of multilinear polynomials, you'll see that, once you evaluate, if you're evaluating the multilinear extension polynomial at a random point, you'll see that each and every one of those n terms of the sum is non-zero. So there's one term of the sum for, each entry of the vector you're taking the extension of, and each and every one of those entries contributes something non-zero to the sum. It's seeming like, I'm imagining now a visualization I can try to put into the book where I take an arithmetic circuit, I write down its gate by gate evaluation, right? And then I actually sort of write down for each layer of the circuit what its multilinear extension looks like. And I sort of point out, illustrate somehow that, as you go layer by layer through the circuit in the GKR protocol, the prover is forced to make a claim about, a different randomly selected point in that multilinear extension for each layer. That would probably help illustrate some of these concepts, I guess. It's just annoying, it's literally hard for me to make those pictures because, the multilinear extension vectors have an entry for every field element. So, unless that field is really, really, really tiny, I just can't, I can't fit the whole vector of representing the multilinear extension in the picture. But anyway, okay. And this is only valid because the multilinear extension is unique and we're evaluating at a random field value that's outside of the hypercube. So any different gate combination would lead to different multilinear extensions, right? That is correct. I mean, something very similar. It's something similar to identical can also happen with other low degree extensions, not just multilinear extensions. It's just when you do use the multilinear extension, a lot of nice other things happen, right? So like the distance amplifying properties of, low degree polynomial extensions, you only need low degreeness. Short Zippel will then tell you stuff is distance amplifying. The reason we use multilinear extensions is a lot of nice algorithmic things happen to ensure that like the prover is very fast when you use multilinear extensions. And that's because of like nice structure in these Lagrange interpolating expressions. So in principle, I think like you could sort of redesign the GKR protocol to potentially use, non-multilinear extensions of the gate values at each layer, but it wouldn't be totally trivial to do it. I don't know. The multilinear things do have some nice properties. It's just the one thing I want to be clear about is like the distance amplifying nature of the extension encoding only requires low degreeness. But there's other nice properties of multilinear things beyond the distance amplifying properties.
I know we only have a few minutes left. I was curious if could you kind of take us through where we're going? Like from this, extending into, I guess, what are the next steps? What are the abstractions that we're going to kind of be approaching as we go forward?
Yeah, it's a great question, especially, and thank you for asking it. Here we have the GKR protocol, which is complicated and, 15 pages to cover. So the big picture where this is going and what you need to know moving forward is great. I should be discussing that. Okay, so I think the next thing we wind up covering, essentially, important thing is how to take any interactive proof, but the GKR protocol in particular, and turn it into a snark. In a snark, the prover is claiming to know a witness satisfying some property. So this is like some kind of NP complete problem, where circuit evaluation is in P, right? Like the verifier could solve the problem in time linear in the size of the circuit on its own. That's because the input is fixed, like there's some just public input. But in snarks, like the prover knows a witness in its own head that's not known to the verifier, right? So you can't just like directly apply, the GKR protocol for circuit evaluation because basically the verifier doesn't know the input to the circuit that the prover knows. So the next step to see is how you combine the GKR protocol with cryptography to get that snark, to basically make the protocol work, even when the verifier doesn't know the input that the prover, is evaluating the circuit at. So the circuit in that context is going to like take as input the witness and check that it indeed satisfies the property the prover claims it satisfies. Okay, so that's the next step. Okay, after that, we start to look at how you don't need an interactive proof for, you can also get snarks from other probabilistic proof systems like multi-prover interactive proofs and probabilistically checkable proofs and things like that. And after that, we would then cover the cryptographic techniques, like the details that turn these interactive proofs and MIPS and PCPs into snarks, right? So I think that chapter 7 sort of tells you what the cryptography kind of does without going into the weeds of it. And you have to wait till like chapter 11 and up to get into the weeds of that cryptography. Okay, so and once all of that's done, you then wind up understanding like basically all snarks, because almost every snark out there, every snark out there sort of takes some information theoretically secure proof system like an interactive proof or a MIP or a PCP, and some cryptographic object, and puts them together, and that's how you get the snark. So that's why there was a poll about, did we want to talk about the cryptography first or the information theoretically secure proof systems first? And people voted for the information theoretically secure stuff, but maybe now that the GKR protocol has turned everyone off of that, it's possible and we should take the poll again. I don't know. And somewhere in there, we should probably jump ahead to the final chapter of the book, because that sort of gives the high level overview that I'm trying to convey right now, and explain like the pros and cons of, the different, what's the pro and con of starting with an interactive proof versus a MIP versus a PCP versus an IOP as your information theoretically secure proof system. And then it also talks about what's the pro and con of the various approaches to developing the cryptographic transformations of those things into snarks. So rather than just, continuing to dive forward deep into the weeds, seeing things like the GKR protocol, we should probably take a break to get the big picture discussed. So yeah, anyways, in summary, I think how we'll go forward, but we can discuss it more, is, we sort of next see what the cryptography does. So, what the cryptography does that enables you to take something like an interactive proof and turn it into a snark, right? Then I think we jump ahead to the final chapter, so you can get the big picture of the pros and cons of all of the different choices of the information theoretic thing and the cryptographic thing, and you can take any combination of them you want. And then we continue further into the weeds with either the information theoretically secure stuff or the cryptographic transformation stuff. Was that helpful?
Yeah, thank you. Looking forward to that. I've got to sign off, but one last comment I had was the concept of the witness is something I've encountered before in some reading about this, and it's still very opaque to me what that means, and I look forward to learning more about, I guess, what's the intuition behind that notion in coming sessions.
Yeah, sounds good. And that's I think that's why I'm hoping to talk about that. Essentially, we finished the GKR part. I think we can jump exactly to that notion, which is so important to have clear in your head for the entire rest of the book, because then from there on, we'll be talking really about snarks and not just like interactive proofs. So there'll be this notion of a witness throughout. Yeah. Cool. And then, I guess the last thing I'll say, given that I feel like still no one is understanding the details of the GKR protocol, unfortunately, is it actually might be the single most complicated protocol in the entire text. So it's maybe unfortunate we're seeing it first. The reason we're seeing it first is because interactive proofs are sort of the simplest model to talk about first, but that doesn't mean that every interactive proof protocol is the simplest protocol to talk about. And you really won't need to know the details of the GKR protocol at all moving forward. In order to turn it into a snark, there's only really one property of the protocol we need. And that is that the only information the verifier needs to know about the input to check the prover's claims for validity is a single evaluation of the multilinear extension of the input, at like a randomly chosen point. This picture that got posted into the chat, we should revisit after we read the final chapter of the book and have a discussion about things like that. Like you can basically, like all of the details that we discussed today and that, people are confused about, like, obviously it's great if you understand them, but if you don't, it really doesn't matter. The only thing to grok, which a priori sort of seems magical, but what you sort of do get in a sense of the techniques, like, should seem very natural, is this thing that I just said, that like the verifier like doesn't need to know the full input to the circuit. It literally like can ignore the input as long all it winds up doing is needing to know a single evaluation of the multilinear extension polynomial of the input. So I can stick around a little longer, but I'm sure most people have to go. So thanks as always. And I guess there'll be administrative updates in the.
I have another question. So is the circuit size in every layer always always 2 to some n?
Yeah. So it certainly makes it far more convenient if it is. But there are a bunch of games you can play to get around that issue if it's not. Essentially, it's always like free in terms of costs and like not terribly difficult in terms of implementation annoyances, to just kind of pad each layer with a bunch of gates that evaluate like are just fixed to the value 0. Yeah, I guess I could put it that way. And like a lot of the costs of the protocol like will not change at all in that sense. Like, you know, in principle, that can kind of almost double the size of the circuit, you know, because like if each gate has, you know, 2L plus 1, if each layer has 2L plus 1 gates in it, like I'm saying, well, just pad it to the next power 2, and that's almost doubling the size. But if the padding is all zeros, then like the padding sort of, when you look at the Lagrange interpolation expressions, the padding just literally doesn't contribute to any of the polynomials involved in the protocol. So there's no extra work anyone is doing to deal with them. So it's only like a conceptual thing that you're even treating that padding as being there. Was that enough information?
So it's just for convenience.
Yeah, so like describing the polynomials, conceptually, certainly it's, you know, just think of them as all being powers of 2. And then like in practice, if they're not powers of 2, it turns out like nothing really changes. Like, you know, when you look at, you could probably write your implementation just like assuming powers of 2. And how do I want to say this?
In the book, there's a figure. I think it's on page 54, but maybe there's different version of the book. It's a figure 4.10. So
Describe the figure, please, for the caption or something.
like in the input layer of the figure, there's 2 threes. So
okay, yeah, I'm looking at it. Yeah, got it. Mm-hmm.
it is a reason. What it is a question I just mentioned, the reason why there's 2 threes and not just 1 3. Like, can we?
Yeah, no, it's not. I just wrote down some like arbitrary input there that made the multilinear extensions work out. Now with circuits as opposed to formulas, their fan out can be as big as you want. So there's no real reason to include multiple copies of a single input. You know, break it into like 2 different inputs and, you know, just force them to be like the same value or something. When you could just, you know, stick an extra outlier of the one input without copying it. So, you know, that's not why I did that. But you could imagine, like, in terms of your question relating to this figure, you could ask, well, what if you only had 3 inputs instead of 4? So what if the input was, I don't know, 3 2 1 instead of 3 2 3 1? Like, just what would you do? And I think what I would say is like that. I think that's like kind of your question. And what I would say is you would add, you know, sort of conceptually, you would add a 4th input to make it a power 2, but you would set that input to be 0 and connect it to nothing. You know, there'd be no wire leaving that input. And
so this figure can be done by just connecting the first 3 to the third to where the second 3 is connecting right now.
Yeah, so you could do that, and you could make that change, and it would not change the the outputs of the circuit on this input. But if you were to change the input so that, you know, the second 3 was a 4, you know, then that change to the wiring you're proposing like would make a difference then, right? So, you know, you're imagining, you know, typically when we're talking about applying the GKR protocol, you're imagining that like, you know, first the prover and verifier agree on the circuit of interest, right? And then later, you know, the verifier tells the prover like, hey, here's the input I want to evaluate the circuit at. So you don't want to, you know, start making changes to the wiring of the circuit that will change the the output to the circuit on some inputs, but not others. If you don't know the input to the circuit, at the same time, you're deciding what the circuit is, So there might be some applications where sort of the circuit and the input to the circuit become known at the same time. And then you could, happily simplify the wiring pattern, taking advantage of certain like repetitions in the particular input you care about. Sure.
Oh, okay. I was just confused about like why not just directly connect the third gate to the first three if that doesn't change anything. Oh,
Now on this input, you could do that and it wouldn't change anything. I mean, it would change like the messages in the interactive proof because you've changed the circuit, but it wouldn't change the output of the circuit on this input. It's just, we're envisioning a situation where the prover and verifier have there's some circuit they care about, and then like later they learn the input. And like, on that input, there might have been some like, simplification to the wiring pattern you could have made without changing the outputs of the circuit, but like they didn't know that what the input was when they settled on the circuit, if you will.
okay. Another question is just about my previous question in the chat. So like about the verifier, why the verifier can run in OS time. So I thought the verifier has to evaluate addition and multiplication himself or herself. So isn't it like should be just the same as the verifier if the verifier same as the prover if the prover has to evaluate addition and multiplication in as log s time?
Yeah, great. So, okay. So yeah, just a quick clarification to anyone listening who wasn't reading the chat. I'll rephrase your question. I'll repeat it. In the GKR protocol, the verifier, kind of in its final check at the end of each invocation of the symcheck protocol needs to evaluate like the multilinear extension of the addi and multi functions. They're kind of like capturing the wiring in the circuit, at a random point. And so the question is like, how fast can the verifier do that essentially? Specifically, why can it be done in time sort of order S, where S is like the number of gates, let's say at layer I and I plus one, versus S log S time. Okay. So if you sort of directly naively apply Lagrange interpolation, it will be S log S time, but a slightly more clever algorithm that's still going via Lagrange interpolation, but just sort of being more clever about how you do it, can get rid of that log S factor. So in the, and so you sort of also ask like, doesn't the verifier, I don't know, you said like the prover runs an S log S time in the 2012 paper, that we were talking about, and so you're asking like, should the verifier have to take at least as much time? So in general, like the verifier, like the prover has to do a lot more stuff, right? The prover has to, each message the prover sends in the protocol involves like a giant sum of, whatever you're applying sum check to at that point in the protocol. And so that's a bunch of stuff the verifier does not have to do. So, like the whole point in the interactive proof setting, when we're not dealing with snarks with cryptography and things, is to ensure that the verifier is actually saving work, is much faster than the prover. So there's work the prover has to do that the verifier doesn't have to do. But in fact, it's now known how to make the prover run in time, order S without the extra logarithmic factor too. It's just in that 2012 paper, it was not known how to get rid of that log S factor for the prover. It was known. Forgetting the history, I think it was known for the verifier. It just basically, if you're more clever about how you do the Lagrange interpolation, you can get rid of the log S factor. The verifier's bottleneck is that Lagrange interpolation. It just has to evaluate add and mult at a single point, and like that's kind of the most difficult thing it does in the whole protocol in a sense. Did that help? I don't.
So the prover has to evaluate die and multi, I don't know, in S log s time, but the verifier can do it in s time.
So so in the 2012 paper, which is not the state of the art result anymore, right? The prover does more than evaluate added malt at a random point. Right? It has to do that. It has to evaluate added malt is like the same random point the verifier winds up having to evaluate added malt, but it has to do even more than that. So it's certainly known now, and I think it was known even in 2012 that you could always evaluate added malt at that random point in order s time, for any wiring of the circuit. The reason for the extra log factor in the prover's runtime was basically because it was doing more than that. So it was kind of doing something like that in every single round of the sum check protocol, and there's log s many rounds of the sum check protocol. So that's why you were getting s log s time for the prover roughly, is it was spending time like s sort of every one of the log s rounds. Whereas the verifier kind of only has to do it in the final round like once, sort of.
Oh, I see. I guess that's all my questions for now. Thank you.
So just one final question, but this is a little bit off topic, but it's just because I have been playing around with Circum for a while now. And I've seen the proofs that circuits can map any problem in NP complete. Can we dream about a circuit language like Circum being Turing complete, or is it already proven to not be possible?
So I think it's basically known to be possible, like in theory, and has been since at least like the 50s or something. There's general transformation. So this is covered in a chapter of the book on front ends. I forget the numbering now, but it's either 6 or 7 now. There's a whole chapter on this stuff, but the chapter doesn't fully do the literature justice because it's just there's so much, and also it's the transformations are a little bit complicated now, and what else did I want to say? I'm dumping it all into one chapter, so I sort of did my best. But it's known in principle that you can take like any computer program that runs in T steps and turn it into a equivalent circuit satisfiability instance of size like T times polylog T. Right. So I mean that's a complete transformation because you can start with any computer program. Now, of course, like the more complicated, like kind of the primitive operations allowed by the computer program, the grosser that circuit is going to look. And this is sort of kind of what like the tiny RAM work is doing, is it's developing like a very simple computer processor and then like turning it into circuits. Sort of. And Circom is like sort of just I don't know the details of Circom and how it differs in its approach, but it's at the very highest level it's like just doing the same thing. But yeah, in terms of like making this like the circuits like kind of reasonably small in practice, that's what's so nasty and why there's sort of paper after paper sort of about this, and the existing infrastructure is maybe not matching like kind of what's theoretically known in the research literature and stuff. Cool. Yeah. So I'm happy to talk more about that. It's a super important topic. Unfortunately, the book is mainly about like the proof machinery, so there's just one chapter on it. There are, I think in practice today, like in addition to Circom, like people like to use like XJ Snark. And, I have a collaborator who put out a new system, which it's public now, but it's sort of not complete yet. It's called CIRC, CIRC. So I think in the next couple years, basically, like I call these front ends, they're like turn computer programs into circuits, basically, or RNCS or something. I think the existing tooling for that is probably going to hopefully get more mature and better. Because right now, Circom, XJ Snark, that's what people are using, and like they're nice. But my impression is, you could always hope for better tooling, and this is still early days. If that makes sense.
Yeah.
Cool. Okay. Any other questions? All right. Well, there's always the chat. Well, thanks for sticking around. 20 minutes past the end, and I guess look forward to talking more next week. Have a great weekend.
Yeah. Thank you.
Thank you.
Thank you.
Bye.
Bye.